I would like to thank him for doing this. It was really thing and very well understood.
Thank you. Okay, so the great thing about this is we can just remind ourselves what I was doing yesterday. So yesterday I gave you this almost perfect example of this triangular basis theory, which was this nil-Brauer category. So remember that's NB sub T, and the parameter T is either 0 or 1. So this was the slide we had yesterday. But the definition is like incredibly simple. It's just a strict graded monoidal category. And it's got one generating object, which in algebra I use the letter B for it. And when I draw these string diagrams, there's just one single string. And then it's got these generating morphisms, the dot, which is of degree 2, the crossing of degree -2, and then the cup and the cap, which make this B into a self-dual object. And then the relations, they're just written there in that grey box there, so we saw these last time. So it's like, this presentation is kind of one of the cleanest examples of these sorts of monoidal category that show up in categorification. So for me, it's my new first example, because it's simpler than all the other examples in some weird way. And so now, let's see, what else did we do? I told you the basis theorem for morphism spaces in the nil-Brauer category, NBT. Remember, T is 0, 1. The endomorphism algebra of the unit object, that was this algebra Schur Q functions gamma. So that's this sort of dotted bubbles in this story. And then the general morphism space between, remember the objects in this category were just labeled by natural numbers because it's just a tensor product of n copies of the generating object B. And a general morphism space in this category is then it's an infinite dimensional graded vector space. But the key thing is it was graded finite dimensional and bounded below. That sort of makes this whole story work. Without the grading, this would be totally impossible here. I'm going to be telling you about categorification of quantum groups in a minute, and this grading, you get this grading shift functor Q, and it makes all of the Grothendieck groups, or in fact it's monoidal, so it's going to be a Grothendieck ring. The grading shift functor is going to give us an action of Q on that Grothendieck ring, and that's going to be the Q in the quantum groups. Grading corresponds to Q. So that was something that we did, and then once I had that basis, I gave you this very visual triangular decomposition of this nil-Brauer category. So this was an important picture. Remember this triangular basis XHY, because these nil-Brauer morphism diagrams, you can always choose them so that all the cups are at the top and all the caps are at the bottom, and all the crossings and the dots and the bubbles are in the middle. And that's a very visible triangular decomposition. The X part is at the top, the H part, the diagonal part in the middle, and the Y part at the bottom. And this interesting relation in the nil-Brauer category, this dot sliding relation, when you pass to the cartan, which is not a subalgebra but a subquotient, that cup-cap term, that kind of disappears in this subquotient, and so this weird new relation in the nil-Brauer category becomes the usual relation that is very classical in the nil-Hecke algebra. So kind of the feature of the nil-Brauer category is that the cartan parts are just ordinary nil-Hecke algebras for all n. And then from that we got standard modules, BGG reciprocity, all of this. In particular, all the interesting families of modules were all labeled by natural numbers because the nil-Hecke algebra NHN has just one irreducible. So we had these various families of modules, all just labeled by natural numbers. L of n, P of n, delta of n was the standard module. And I wrote down some really crazy formulas. For example, the multiplicity of a standard module delta n in the delta flag for the projective indecomposable P there, it was given by this that you have to expand this as a formal Laurent series in Q inverse. So it's some crazy infinite formula, but it exists. It's kind of remarkable where you get some situation where you even have such a formula. So it's somehow very complicated, but also very simple because it exists, that formula. So that was where we were. And now today I've got to tell you kind of why I care and why this nil-Brauer is really kind of a beautiful object, and why this miracle of having these formulas is even possible. So we've kind of got to start again, and I'm going to tell you just a little bit about I quantum groups. So this is Webster's quantum groups corresponding to symmetric pairs. These co-ideal subalgebras of ordinary quantum groups. Now I've got to admit I know very little about I quantum groups. But fortunately I have Weiqiang as my co-author, so I can get away with it. But so I'm going to just tell you just a tiny little crash course of the very little that I know. The thing is, we're going to be looking just at the absolute easiest of all I quantum groups. I call it, so the upper I, that stands for this involution in this theory. So the U upper I is the I quantum group for SL2. So it's really the easiest of all I quantum groups, U upper I, SL2. I'll just call it U upper I generally. The Satake diagram for this is just a single white dot. So this is the split I quantum group of rank 1. It corresponds to the symmetric pair that's SO2 sitting inside SL2. It's a pretty stupid symmetric pair. This I quantum group is in many ways a pretty silly algebra. So let me just explain you what it is quickly. So let's start with ordinary quantum SL2. Ordinary UQ SL2 generators E, F, K, and K inverse. Just over Q is generic, over rationals Q of Q. And then the I quantum group, I'm just going to call it U upper I, is the subalgebra of quantum SL2 generated by this one special element, B here. B, it's roughly F plus E. As an algebra, it's just a polynomial algebra in B. That's all U upper I is. It's just a rank 1 polynomial algebra generated by this magic element B, which is kind of F plus E here, up to some Q. So that's what it is, as a Q of Q algebra. But, okay, boring as an algebra, but it's interesting because it's a co-ideal of the ordinary quantum SL2, and somehow the incredibly rich structure of ordinary quantum SL2 gives some amazing structure to this very boring algebra. So it's how it embeds into ordinary quantum SL2. It actually has this incredible rich hidden structure, which is kind of shocking. Okay, so of course you know what we're going to do. We're going to be categorifying this I quantum group. This split I quantum group of rank 1, this simplest of all I quantum groups. For categorification, it's always better to work with modified forms of quantum groups. So maybe this is pretty familiar to people. I'm not going to say it very precisely. So instead of working with quantum SL2, the usual quantized developing algebra, I want Lustig's modified form U dot. And roughly what's going on is I replace the K in the usual presentation. I replace it by a bunch of mutually orthogonal idempotents. We're doing SL2, right? So weights are just integers. So for each integer lambda, I'm going to add an idempotent 1 sub lambda. And these are all mutually orthogonal. So this is the modified form. It's just one of these locally unital algebras that I like everywhere. And I don't think I'm going to give you the definition of U dot. Just remember what's going on is that K is being replaced by idempotents. So instead of writing K 1 lambda, you just replace the K, it becomes Q to the lambda 1 lambda. And E E on the right is weight lambda, and on the left is weight lambda plus 2. F on the left is weight lambda, and on the right is weight lambda minus. Remember, so this is SL2. So the simple root alpha, that's the integer 2. And just as quantum SL2 has this modified form U dot, this co-ideal subalgebra, that's our I quantum group U upper I, which is a subalgebra of U, it has a modified form as well. And actually its modified form is a little bit different. It's just a direct sum of 2 ordinary unital algebras. So instead of there being weights labeled by Z, for this I quantum group, actually there are only 2 weights that are interesting, 0 and 1. So it's really Z mod 2 in this case. So the modified form of this I quantum group that we're looking at is just U0 upper I, direct sum U1 upper I. And you see this 0 or 1, that's my parameter t that we had yesterday. T is either 0 or 1 in this I quantum. And what is UIT for t is 0 or 1? Actually, it's not quite a subalgebra of the modified form of the quantum group, because that's a direct sum. You have to replace that direct sum by direct product, so that's kind of a completion of the modified quantum group. And you only take lambda and mu weights, which are congruent to t mod 2. So this completed quantum group kind of splits into two pieces, and the t, that's really a parity, whether you're doing even weights or odd weights. T is fixed, 0 or 1 forever. Okay. So the modified form of the I quantum group ui upper t, it's the subalgebra of that completion for weights of parity t, and instead of b up there, f plus q k inverse e, before I went to the modified form, it's generated by this. This is the modified version of b. So it's f1 lambda plus q to the minus lambda minus 1. The k is turned into that power of q. e1 lambda for all lambda. So it's really an infinite product over all lambda. So that's the gadget we're going to be interested in, u upper I sub t. And this kind of naturally explains why t equals 0 and t equals 1 are the only two cases, because these are the only two cases for this modified form of this I quantum. So, okay. It's still a very boring algebra. ui upper t is still simply a polynomial algebra of rank 1 in this generator B. Okay, so my algebra is a polynomial algebra of rank 1. What could be easier than that? But as I said, somehow the embedding of this I quantum group into this modified quantum SL2 means that it inherits just kind of remarkable extra structure. I've slowly learned a little bit of this. So this is Weiqiang's work with his former student, so Bao and Wang. And they really have developed this totally remarkable theory of I canonical bases. So Weiqiang kind of tells me he works in this I world. So I think so everything Weiqiang does has an I in front of it now. He's much braver than me. I cannot make myself do it. What he does is he writes I quantum. So that's the math I math. And he doesn't even put a hyphen there. So I just can't make myself do that. So every word he now has this extra letter I at the beginning. And I guess I'm just new to the I world, so I haven't got that I can't make myself do it yet. But maybe in a few more years. They've developed this really astonishing theory for all I quantum groups. Working out what the right definition of I canonical basis is, and there's just a phenomenal amount of structure attached to this, and they've done it in total generality. And I'm just going to tell you a few little pieces about this remarkable theory for the easiest I quantum group, this split I quantum group of rank 1. But I just want to emphasize that there's this general theory which where everything's actually totally natural, and I'm kind of messing it up by telling you this special case where I can be a little bit more explicit.
Can you go back to the previous slide? So I'm confused because there's on the last line there's a t on the left hand side, but there's no t in the generated line.
That's correct. The t is here.
So
the t here, it embeds in the half of the completed modified form corresponding to weights of parity t.
So it's generated by b's, but you do this for all lambda?
So b this is really it should be this. It's an element of this product for all lambda. So sorry, my notation there is not very good. It's this for all lambda. And I guess maybe I should have put the 1 lambda over here so that it was.
Yes,
I'm being a bit sloppy in how I wrote that.
So
it's kind of this for all lambda. In this infinite product.
So each component is that term.
in each component is that term, right? So yeah. And because it's I need that for all lambda, that's why I have to go from the direct sum to the direct product. I just kind of want to give you a sense of why T is really the parity of weights that you're looking at. You're either embedding into even dimensional SL2 modules or odd dimensional SL2 modules. Those are the two cases, T equals 1. This canonical basis for the I quantum group somehow is inherited from this embedding. So it actually depends on whether you choose even parity or odd parity. It's very subtle, but in this big general theory for all I quantum groups, that's what falls out. Actually, it's kind of beautiful and very natural. And I'm just telling you this easiest special case. So here's some of the extra structure in this easiest special case, but it's just an application of the whole general machinery in this case. First thing is that there's a non-degenerate symmetric bilinear form on the I quantum group. And so that's this I again, right? Everything's going to have this superscript I, because it's all the I version of it. So this is like Lustig's form on the usual modified quantum group, but this is the I analog, so the form on this I quantum group, and it's kind of special. I'm not quite going to tell you what it is yet, I'll tell you on the next slide. But maybe it's worth pointing out that this generator B of the I quantum group is kind of self-adjoint for this form. So you can pull B from the left to the right according to that. There's a bar involution on the I quantum group. I use C for my usual bar involution. So C upper I is the bar involution on the I quantum group. So that's an antilinear map. Q goes to Q inverse. And it's very simple. It just fixes the generator B. So it's an algebra anti-involution that fixes B. There's a canonical basis. Now, this is called the I canonical basis. Let me put my I back in because that should be there. It's the I canonical basis of the I quantum group. Now, this is much harder to give the correct definition in general. I think this is the remarkable thing that Wang and Wang discovered that's really quite striking. So in this case, it's simply our I quantum group, right? It's just polynomial algebra in B. So it's obviously got a basis, the powers of B labeled by natural numbers. And all the other bases are just going to be labeled by natural numbers. The canonical basis, I denoted P sub n, where n is a natural number. It's meant to remind you that our indecomposable projective graded modules for the nil-Brauer category were P of n a natural number, where it was in brackets, and here it's a subscript. It's just they're going to match. I'm not going to give you the definition of the I canonical basis, but it's just this general definition. And we're doing it in this one example. But it's kind of usual thing. It's invariant under the bar involution. There's also a PBW basis for the I quantum group, and that I just denote delta sub n. It's the same delta as I use for my standard modules, but with a subscript and a bracket. So it's another basis for this I quantum group as a Q of Q vector space. Actually, I guess that's reasonably new. The PBW basis, it's an orthogonal basis for the I quantum group with respect to this bilinear form. You can explicitly write down what the bilinear form is on that orthogonal basis. And the canonical basis, so let's go down here. The PNs, the I canonical basis elements, they actually span an integral form of the I quantum. So I put an extra subscript Z there. So this is an integral form over the ring ZQQ inverse for the I quantum group. So it's free as a ZQQ inverse module with basis given by the I canonical basis. When you multiply two I canonical basis elements, you just got coefficients in ZQQ. So this is really a remarkable integral form, which is really not trivial at all. Even though this is just a polynomial algebra over Q of Q, this integral form is much more subtle and interesting. The I canonical basis element Pn can be expanded in terms of the PBW basis. What you find is that Pn is delta n plus a combination of smaller deltas, smaller PBW basis elements, but the coefficients, there's one, Pn is delta n plus lower terms. The coefficients there not polynomials in Q inverse, they're formal series in Q inverse. They're strictly negative powers of Q, formal power series in Q inverse starting at Q inverse. And they're really infinite sums. In fact, the theorem I wrote down last time, where I gave you this formula for the multiplicity of delta n in delta flag of P of n, and I actually wrote down that rational function and I said expanded as a power series in Q inverse. It's exactly that number. So it really is this infinite power series in Q inverse, just because we happen to be able to compute it in this case.
If you take the bar involution on the PBW, is it upper triangular?
Yes, but the problem is somehow the P of n's are a basis over ZQQ inverse, over this Laurent polynomial ring. The delta n's are not a basis over Laurent polynomials. They're a basis actually you have to complete. They're a basis over Z formal power series Q inverse. And this is sort of a new behavior that happens in these modified quantum groups and I quantum groups. It's not like the canonical basis on the plus part, where you can use Lustig's lemma and you have standard basis and canonical basis, and once you know the triangularity of the bar involution, you can define the canonical basis from the standard basis and compute it algorithmically. Here that just doesn't work, because the PBW basis is actually only a basis for a completion where you need these formal Laurent series in Q inverse. So you actually have to start by coming up with some other definition of the I canonical basis, and then the PBW basis kind of comes afterwards. And you see these transition matrices, but it's harder to. I can't give you a characterization of Pn as bar invariant triangular to delta n, but that doesn't work in this. It also doesn't work for ordinary modified quantum groups. But nevertheless, because Pn is delta n plus Q inverse stuff, albeit infinite, the fact that the delta n's are an orthogonal basis lets you understand how the I canonical basis looks like with respect to this bilinear form. It's almost orthogonal. I mean, it's not orthogonal, but kind of in the limit as Q goes to infinity, it's orthogonal. So the inner product P and delta n, it's 1 if n equals m, 0 otherwise, plus horrible terms that are divisible by Q inverse. So this almost orthogonality of the I canonical basis comes from the triangularity to the PBW basis, which is genuinely an orthogonal basis. That's kind of an important point later. And I'm not going to give you the correct definition of Pn, but because we're in this very small rank 1 case, it turns out that you can calculate Pn explicitly. It's great when you do SL2 or something like this, because the miracle happens that this thing that's normally impossible to get your hands on, this I canonical basis, it's a small case, you can work it out. And let me just give you the recurrence relation for Pn, which was worked out by Berman and Wang. So P0 is just 1, that's our bottom I canonical basis element. P1 is just B. But then after that, P2 starts getting more complicated. But here's the recurrence relation. So this, I'm going to put this circle around it. This is very important, and it's a very simple, beautiful recurrence relation. Bpn, it's quantum n plus 1, Pn plus 1, plus, if n is congruent to T mod 2, so there's some weird parity thing where the parameter T comes in, you get a quantum n Pn minus 1 showing up, depending on the parity. It's a very, as these things go, that's a dream when you have a nice recurrence relation to your I canonical basis. Everything's labeled by natural numbers. It's sort of very cute, sort of simple setup. So that if you like, that's the definition of the I canonical basis, but it's not. The definition is much more clever, and then it was explicitly computed in this case. This recurrence relation follows from that computation. I also mentioned the PBW basis. That also satisfies a recurrence relation. That's up there. This doesn't depend on T. The I canonical basis depends on the choice of T. And there's the recurrence for delta n. B delta n is quantum n plus 1, delta n plus 1, and then there's some delta n minus 1s, and that's actually a formal Laurent series in Q inverse there, so that denominator which you have to multiply. So that's the kind of those recurrence relations are sort of a cheating way for me to define those guys. I've not given you the correct general definition, work it out in this small case that they satisfy those recurrence relations. Alright, so now I want to go to categorification then. We've got this I quantum group, U upper I, subscript T, and the Z there because we're working with this integral form. Depends on T is 0 or 1. Because I'm now telling you how to categorify this I quantum. Well, of course, it's going to be categorified by the nil-Brauer category, NB sub T. So let's start with the bilinear form. This is this bilinear form on the I quantum group, where the PBW basis was orthogonal and the I canonical basis was almost orthogonal. It was kind of orthogonal in the limit as Q goes on. So here's where you actually have to use the definition of this bilinear form, which I didn't tell you, and you have to calculate it. And it's a little bit of a complicated calculation, but elementary. By explicitly calculating it, you can just write a simple combinatorial formula for the inner product, b to the n, b to the m, just the monomials in the generated b. So this is the bilinear form on monomials. And here's the combinatorial formula. Maybe you can't read it. So the inner product, b to the n, b to the m, this is not an orthogonal basis. The inner product is 0 unless n plus m is even. And if n plus m is even, this is what you get from kind of doing some recurrence relation-y sort of computation of this inner product. It's kind of elementary, but very important step. You get this power series term at the front because you have to expand that in terms of Q inverse really. So it's 1 over 1 minus Q to the minus 2, and then that's m plus n over 2. M plus n has to be even for it to be non-zero. And then the interesting part, the combinatorial part, you get a sum over C. C is going to sum over all chord diagrams. Chord diagrams with m plus n marked points. I'll do an example on the board in just a second. And then it's Q to the twice the number of crossings in the chord diagram. So I'm just going to do like a really trivial example. B squared, B squared. That's the bilinear form for B squared, B squared. So m and n are both 2, so m plus n is 4. According to the formula, it's that, and then it's the sum over chord diagrams with 4 marked points. And what is it? It's Q to the 2 times number of crossings in C. So what's a chord diagram? This is somehow a classical thing. You take a circle and you put your 4 marked points, 1, 2, 3, 4. So they're marked. I'm not going to number them, but they're just points 1, 2, 3, 4. And then a chord diagram, you just got to join those points up with chords, right? So what could I do? I could join them that way, or I could join them that way, or I could join them that way. This is such a baby example, but now I think everyone knows what I mean by a chord diagram, up to isotope. It's a common real thing. No crossings, 1 crossing. So what do I get? There's 2 of them, so they contribute 1 to this power of Q. This contributes a Q squared, so it's 2 plus Q squared. It's literally that elementary, but these chord diagrams kind of you have to kind of come up with some cunning recurrence relation to see that you get this form. It's kind of a very fun piece of math circle sort of combinatorics. It's a fun game. Lemma. The inner product Bn Bm given by this explicit formula of chord diagrams has something to do with the nil-Brauer category. So this is our nil-Brauer category NBT, and I'm looking at object N and object M there. So this is just this morphism space in the nil-Brauer category. The basis theorem that we proved shows that's a free gamma module, and there's an explicit basis. So you count with Q's because it's graded. You work out the rank of that as a free gamma module. It's exactly this inner product. This is sort of what I actually think I think this really goes back to Aaron Lauder's categorification of SL2 and Kavanagh and Lauder's generalization of that. But I think maybe the arrow out. I've kind of maybe Michael is where we kind of learn how to count these diagrams and look for these diagrams counting relating to bilinear forms or quantum groups. So this is the analog for this simplest I quantum group. And I mean, what is this? So we're looking at morphisms from 2 to 2 in the nil-Brauer category. Well, what are the morphisms from 2 to 2? Well, you can either have the identity morphism, or you can have a cup cap, or you can have a crossing. And then you remember you can pick marked points where you can put some number of dots on each string here. So these are these kind of reduced diagrams. Those are that's the basis for this morphism space in the nil-Brauer category as a free gamma module. And remember, dots are degree 2, so they give you this 1 minus, and my q is negative of the degree, so that comes from the 2 dots. It contributes this factor, and then this factor, well, that and that, you just see those are those 2 chord diagrams, right? They're degree 0, there's no crossings, and this crossing in the nil-Brauer category, you just see that's that chord diagram, and the crossing is degree minus 2, so when I go to this convention, it's q squared. It's just literally that visible. Once you see these chord diagrams, you should see chord diagrams as kind of just, it's just kind of closing up one of these nil-Brauer morphisms by putting a circle around it. But somehow chord diagrams comes naturally when you view this bilinear form. So that's your first clue that there's some connection between this I quantum group and the nil-Brauer category. The rank of these Hom spaces in the nil-Brauer category, which follows from this basis theorem that I explained last time, recovers these chord diagrams, and which also miraculously count, give you a way of writing this bilinear form on the side quantum. It's a simple combinatorics, but it's kind of cool with it when it works. Okay, so now you can probably guess the theorem now. We're kind of getting there. So I'm going to tell you about K0. Like I was doing last time, I kind of like to think in terms of modules. So instead of working with the nil-Brauer category NBT, I'm going to work with its path algebra. You've probably got used to that. That's why I like these locally unital algebras, path algebras of some k-linear categories. So, and I just, for short, T is fixed always. I just write NB in ordinary Roman font for the path algebra of the k-linear graded category, script NB of T. Let's remember, this is the direct sum of all the morphism spaces. And then the identity morphisms give me mutually orthogonal idempotents, making that path algebra into this locally unital graded algebra. We talked last time about how it's graded finite dimensional and bounded below, and that was why I was able to get this nice theory of standard modules, BGG reciprocity, and so on. So we're going to be looking at the category NB Gmod, graded modules for nil-Brauer. Actually, finitely generated projective graded modules now. So PGmod, finitely generated projective graded modules for nil-Brauer. And the theory last time from this triangular basis theory, we classified the indecomposable graded projective modules. These were these modules P of n for n a natural number. And so this labeling by natural numbers, it was kind of immediate when you immediately see this triangular basis with Cartans being nil-Hecke algebras. So nil-Hecke algebras have one simple module to gradient shift. It gave us this labeling set n as labeling indecomposable projective modules for this nil-Brauer category. So those are the PNs, and you remember there was also the standard module delta n, which was like the top delta in the delta flag of P of n, and then the standard module had irreducible head L of n, and that was my labeling of the irreducible. So that was all from last time. Another thing is because the nil-Brauer category is monoidal, you've got this monoidal product, which I use star for. By going to the path algebra, I've kind of forgotten the monoidal structure, but you get it back again when you realize that it induces a monoidal product on the module category. So this is, I put a little circle around that. That's the thing I call the induction product. You can call it day convolution or some sort of convolution product, or it's got lots of different names. But it's just, I think I talked about that a little bit on Friday, the definition. So you just think about the monoidal product as being, it gives you an algebra homomorphism from NB tensor NB to NB, and then you just induce along that algebra homomorphism, and you get the induced induction product on the graded module categories. So it makes that into a monoidal category. I think I said it last time, but kind of a subtle thing here is, unlike maybe if you're used to this for like symmetric group or something, that's the first time I saw these induction products where it's bi-exact. In this general framework, these induction products are not bi-exact at all. They're kind of difficult, quite hard to understand. But they're good on projectives. On projectives, it's just extending the usual monoidal structure on the original category. And then I'm going to write K0NB for just the split Grothendieck group of this category of finitely generated graded projective modules over NB. So we know immediately that that's a free ZQ inverse module with basis given by the isomorphism classes of the indecomposable projectives. So we're already kind of in a good place. And because there's this monoidal product, it's not actually it's not merely a ZQ inverse module. It's actually a ZQ inverse algebra. So I'll call it the Grothendieck ring of this monoidal category. So that's K0NB. So it's free ZQQ inverse module. It's got basis the isomorphism classes of these indecomposable projectives P of n that we classified using our triangular theorem. And then the theorem, of course, you all know the theorem right away because I've been building up to it for a while. This Grothendieck ring K0NB of our nil-Brauer category, depending on the parameter t, is isomorphic to the integral form for the I quantum group, depending on t, with the isomorphism class of the indecomposable graded projective P of n matching the I canonical basis. So that's always the model. And we're in this like honestly easiest possible case. The proof is hands-on. That's kind of what's cool when you do some little baby case like this. It's not a trivial case. But it's kind of doable just by kind of brute force. So I guess the statement you say is that the nil-Brauer category categorifies the split I quantum group of rank 1. Just the same way as Aaron Lauder's Kac-Moody 2 category for SL2 categorifies the modified form of SL2, or the more general Ivanov-Lauder-Ruquier Kac-Moody 2 categories in general categorify symmetrizable Kac-Moody algebras. So this is the first simplest I quantum group. It's categorized by this very rather beautiful nil-Brauer category that in many ways is even easier to see. Under this isomorphism, on K0 you have this Cartan bilinear form, right, which is just taking rank. So if you take finitely generated projectives P and Q, you just look at HOM from P to Q. That's a free gamma module, and you take its graded rank as a free gamma module. I write angle brackets PQ for that. That's this Cartan form on K0. So this is a sesquilinear form because it's antilinear in the first argument, because that's the contravariant spot of the HOM. It matches the bilinear form on the I quantum group, but of course I have to twist it by putting the bar involution into the first argument to turn that from symmetric to sesquilinear. So that's kind of part of the theorem, is that the Cartan form on K0 exactly matches this modified version of the bilinear form on the I quantum. I want to say just like 2 minutes of how this is proved, because well, we tried all sorts of ways, and in the end the most naive way was all we were left with, and it turned out that it worked after all. We didn't want to do it this way. It looked impossible for several months, but all other methods failed. We ended up coming back to the most naive way. Remember the recurrence relation for the I canonical basis. Bpn is n plus 1, pn plus 1, and then half the time you get a lower term, which is quantum n, pn minus 1, depending on parity. So how's the theorem proved? Well, we explicitly write down some homogeneous idempotent. idempotence in the algebra NB. Some idempotent endomorphisms, and I call them E sub n. So this is going to be an endomorphism of B to the n. I'll show you what it is on the next slide. But we explicitly write down a bunch of homogeneous idempotents. And then we show that if you take the nth idempotent En and you multiply it by the generating object B, so B star En, well, we decompose that as a sum of mutually orthogonal idempotents. There's two cases according to parity. In one case, you get a sum of n plus 1 mutually orthogonal idempotents. And these are the notation I'm not quite going to give it to you. ER comma n plus FR comma n. R goes from 0 to n. And we show that each of those is conjugate to the next En plus 1 by units of appropriate degrees, so that it matches the recurrence relation. Or in the other case, you actually get n plus 1 idempotents ERN, and then another orthogonal sum of n idempotents, these FSNs. The ERNs are conjugate to En plus 1, and the FSNs are conjugate to En minus 1. Totally crazy explicit calculation with homogeneous idempotents, decomposing BEN as a sum of mutually orthogonal idempotents, matching the recurrence relation for PN. It's literally the most crazy way of proving anything. It's all we and then if you look at this left ideal, nil-Brauer left ideal generated by the idempotent En, there's a degree shift in there. We show that this is actually isomorphic to the indecomposable projective module P of n. And that's almost easy, but you have to prove that En is primitive. Once you can prove that this En that we magic up satisfying the right recurrence relation is a primitive idempotent, it's pretty easy to see that En is indeed the left ideal that it generates is this indecomposable projective Pn. And to prove that, well, you use the Cartan form. You see, somehow, once you've matched this recurrence, and we know from the lemma, where was my lemma? A lemma way back there. We know we can kind of calculate Cartan form by using the bilinear form on the I quantum group. And these PNs, they satisfy the same recurrence as the I-canonical basis, which we knew were almost orthogonal. That translates into exactly what we need to prove the primitivity of these idempotents. That's kind of the way it goes. Because that almost orthogonality tells you that the degree 0 part of the endomorphism algebra of this left ideal is one-dimensional, and that's the primitivity. So this combinatorics of chord diagrams is buried in the proof of the indecomposability. So I've got to show you these idempotents because it's like suddenly you're doing the most naive thing. We really thought this was too hard. We were trying all these other more fancy ways of proving this, and they all failed. It was kind of shocking. It's a long piece of work, and we ended up with nothing left but the most naive method. And so we literally wrote down these idempotents. So this is what the E's are. E0 is just the unit. E1 is just the identity endomorphism of B. E2 is just a crossing with a dot. E3 is the longest element of S3 in the nil-Brauer category, and then there's kind of rows worth of dots. E4 is the longest element. These are probably totally familiar for you because these are also primitive idempotents in the nil-Hecke algebra. You've seen these sort of diagrammatic way of thinking about Schubert calculus. Remarkably, those same guys remain idempotents. The relations are completely different in the nil-Brauer category. They're much more complicated. This dot sliding is very, but amazingly, the same elements are idempotents, primitive idempotents in nil-Brauer. And then you have to play this inductive game, right? So you start at the beginning and you start with E0, which is just the unit object, and you've got to work out what B does to each En. You've got to decompose BEN in terms of more idempotents, a mutually orthogonal idempotent. So BE0 is just E1. I can do that case. BE1. E1 is just a single string, and I'm tensing it with B. So that's BE1. It's just the identity. By the relations, by this dot slide relation, the identity, it's that crossing minus that crossing plus that cap. So this is still easy, could do this case long ago. And then it depends on whether the parameter is 0 or 1, exactly what's going on here. This is our decomposition of BE1 as a sum. If t equals 1, it turns out that all three of these guys are mutually orthogonal idempotent. So you get this sum of 3, which is what you want. If t equals 0, that's not true. I mean, remember the bubble is t. So you can sort of see that when t is 1, it follows immediately that that's an idempotent. But when t is 0, that's a nilpotent, right? It squares to 0. So what you do is you find that, okay, well, if you put those two guys together instead, you get a sum of 2 mutually orthogonal idempotents, and that's what you want. This is the end of triviality, but you know, you feel that. And then you have to do the next case. So this is what happens when you do BE2. So that's E2, and I put an extra string on the left. And when you write this out, you find you get the sum of all of these guys. It's already now not quite a trivial. There's too many choices, so it's not so easy. When t is 0, you find that all 5 of these are mutually orthogonal idempotents, and you're getting exactly what you want. And when t is 1, you find you have to kind of group these guys together, and you get a sum of 3 mutually orthogonal idempotents. And it's kind of, and the pictures are not very important. I just wrote the next case just for fun here. When you do BE3, so when you compute this guy with 4 strands, you do a computation and you find it's the sum of these pictures. And when t is 0, all of these guys, like this guy here, I mean, it's already quite hard, even if I give you this, to see what pattern is going on. And of course, you've got to do it in general. So for a long time, I despaired of being able to do that. But in the end, we sort of see it with better. So it's a bit miraculous that you can do this. It's quite non-trivial. And let me just finish up with my last slide question.
So for the previous slide, why don't you just go ahead and do all of these up? Write it?
Go for it. I mean, somehow it's literally on the edge of what I could possibly do, and there is a pattern, and there's a reason there in the middle and at the top. I mean, in the end, we had to develop some analog of this thick calculus that we learned from Michael and Aaron and co. So we developed some thick calculus, and that makes this. You can then start seeing patterns a little bit better, but it's kind of miraculous to this person. Very quickly, one more little bit of structure. Starring with B, that gives you a functor from the nil-Brauer category to the nil-Brauer category. It extends to a functor B from graded NB modules to graded NB modules, basically induction along that functor. And because the object B is self-dual, this functor, I call it a projective functor. It's a self-adjoint functor, so it's exact, it takes projectives to projectives, finite generations preserved. So this is this generating object of the nil-Brauer category. It gives you this projective functor between modules. And if you think what the induced map is on the Grothendieck ring, of course it's just categorifying multiplication by the generator B of the I quantum group. So the very last theorem, standard modules categorify the PBW basis of the I quantum group. So here's a simple theorem that lets you see that. If you apply this projective functor B to the standard module delta n, you get this short exact sequence where the quotient is a direct sum of n plus 1 copies of delta n plus 1. This is matching the recurrence relation from the PBW basis that I wrote down earlier that you didn't really quite see. And the first term you get this infinite direct sum. That was the 1 over 1 minus q to the minus 2 in the denominator of my recurrence relation. So you get this infinite direct sum of delta n minus 1s. So it's kind of like a two-step delta flag, where you've got n plus 1 of them at the top, and then you've got this infinite number of them at the bottom. This is just one of, again, the example of where you're not in an Ethereum world anymore. You really have to allow, I mean, this is a finitely generated module, but it has this submodule there's an infinite direct sum of standard modules. So you kind of, the theoreme's gone wrong. It's kind of, for me, that's the scariest thing about this subject, is you have to start working with non-finitely generated modules. It's kind of amazing what it's doing. Okay, so I'm done. I just put up a few references here. These slides, I think they've already posted them now on the conference website, so you can see them. So the main theorem is this last paper, which we just posted to the archive on like Thursday, and it's got this theorem about the categorification. This previous paper, which we posted to the archive like last Monday, that's the paper where we proved the basis theorem. I've got to emphasize how that basis theorem is literally the hardest thing. Going from this nil-Brauer category to proving this basis theorem, sometimes we call that non-degeneracy. I mean, we have a method, but it's just an utterly insane calculation, and I just thought I'd leave you with one page from that first paper. Thank you.
Any questions, comment?
Yeah, I have one. So what if you replace the I-quantum group with another I-quantum group?
Yep.
Do you have any ideas about what the K's are all?
We believe that we should be able to do all quasi-split I-quantum groups.
Okay.
That's when there's no black nodes in the Satake diagram. And that somehow, that case, you could certainly guess what the appropriate 2 category is by starting with the rank 1 cases. We've kind of now got all the quasi-split rank 1 cases we have a handle on, and it's kind of gluing those together. And there's a totally natural conjecture for what the right 2 category is. And somehow, I think the sticking point to being able to prove it is actually proving these basis theorems. It's already very hard in this case. If you go outside quasi-split, I was very hopeful, but Weiqiang's been teaching me some more, and I've lost all hope. I don't think outside quasi-split I-quantum groups seems to be very hard to even have a reasonable guess.
Do you categorify the co-ideal structure, or is it just the algebra?
It's just the algebra. I mean, the proof of this basis theorem, actually, it involves a certain monoidal functor from the nil-Brauer category to some completion of categorified SL2. And this functor, it resembles, B goes to E direct sum F. It resembles the embedding of the I quantum group in the modified full quantum group. But in a very weak way, you have to localize. And so somehow that's kind of a shadow of this embedding, which is the co-ideal structure. But all it's used for is to give us some way of establishing linear independence in this basis theorem. We embed into something that we know. But it's nothing. It's not what you. It's a very weak statement because of the need to localize this thing. So
the naive question then, like, isn't the algebra just a polynomial algebra and one generator?
Yeah. But the integral form is not.
So then you right.
And all this rich structure, all these formulas I gave for like decomposition numbers and graded dimensions and irreducibles last time, they're highly non-trivial. You really wouldn't ever dream that was even possible because they're such complicated formulas. But I know it's just a polynomial algebra in one variable, but it has this rich structure that it's somehow induced by its embedding into quantum SL2.
For the so this thing is non-Noetherian as you described. Is there like anything analogous to like a BGG resolution? I guess it would have to be infinite.
It's a lovely question. I don't have an answer. I think it's a great question. You look back in like some of the literature on chord diagrams are kind of classical. You can find lots of combinatorialists studied them like 50 years ago, and there's some awesome identities for chord diagrams with signs in, and my dream is that there's some BGG resolution that explains these combinatorial formulas counting chord diagrams.
So do you expect a categorification for some modules or I-quantum group?
Yeah, I mean, this is rather a boring I-quantum group. The only modules that you really see are coming from the finite dimensional irreducible SL2 modules from this embedding. And they will be categorified by cyclotomic quotients of this I-quantum group. We didn't work that out, but that's what I expect. It should be that. But they're not very interesting modules, right? They're just strings. But
So maybe higher rank or?
well, okay, but you know, so now we've got to prove something in higher rank. It's not so easy to prove anything. It's easy to come up with conjectures in higher rank, which we have.
Can you observe the relative group symmetry from this categorification?
I have no idea.
With another few years.